Swayam Prabha. Digital India. Educated India.
Welcome back. Last class we solved this particular problem which is shown in the slide, and we are going to continue in this lecture and going to solve yet another question. The question here is, for the pumping setup shown in figure below, this figure, estimate the power required and the pressure at the suction side of the pump. We see that the atmospheric head here is 10 meters and we have to assume both the major and the minor losses. You see there are two pipes, all right, and these things are given. AP, the diameter of the pipe is given, the length is given, the friction factor for each of these pipes is given. Okay. So, how do we solve this? We have to estimate the power required by this pump and pressure required at this suction side of the pump. All right. So, we will continue with (11). So, static head is 110 minus 95. You see that is the static head, if you remember the figure, and that is 15 meter. Velocity in the pipe 1 would be Q by A1. The pipe 1 was before the pump, pipe 2 was after the pump. Therefore, V1 Q is given as 20 liters per second. So, it is 0.02 and area is pi by 4 and the diameter is also given 0.15. So, it will come out to be 1.132 meters per second. Similarly, for the delivery pipe, that is velocity in the delivery pipe, this is a suction pipe and V2 is the delivery pipe. We can A1 V1 is equal to A2 V2, and therefore, V1 can be written as D1 square by D2 square, and therefore, 1 or you can do also Q by A2, 15 by 12, D2 was 12, and therefore, it will come to be 1.769 meters per second in the delivery pipe. Okay. So, the major loss in pipe 1 will be F1 L1 by D1 into V1 square by 2G. F1 is also given in pipe 1, length is 20 meters, it is given, diameter we already know 0.15 meter, into V1 we found out 1.132 whole square divided by 2 into 9.81, and this comes to be 0.174 meter. Okay. So, there will also be inlet loss, and that is 0.5 into, this is the minor loss, V1 square by 2G. So, 0.5 into 1.132 whole square by 2 into 9.81. So, 0.033 meter. All right. So, this was the losses in pipe 1. we are going to see the HF2. So major loss in pipe 2 will be F2 L2 by D2 into V2 square by 2G. So F2 is also given 0.02, length is 300 meters, that is given, into D2 was 0.12 into 1.769 whole square by 2 into 9.81. That comes out to be 7.97. Similarly, there will be a loss at exit, and at exit it's simply V2 square by 2G because K here is 1. So 1.769 it is 0.160. So total head loss is going to be 0.174 plus 0.033 plus 7.975 plus 0.160, and this is going to be 8.342 meter. Now the head delivered by the pump HF will be static head. First it has to overcome this static head plus the losses. So it's going to be 15 plus 8.342, that is 23.342. meter. Therefore, the power delivered by the pump is gamma QHF, that is the total head. So 9.79 into Q is 0.02 into 23.342 kilowatt. If you find 4.7 kilowatt. Okay, so the first part we have got this as the answer. All right, now we also have to find the pressure at the suction side of the pump. So for that we are going to use the Bernoulli's equation and also taking the head loss into account. All right, so part B will be solved by energy equation between reservoir A and pump B. So let PS be the pressure at suction side of the pump. Then we put the Bernoulli's equation. 95 plus 0 plus 0 will be equal to, the pump is at Z is equal to 100, and if the pressure PS by gamma plus V1 square by 2G plus losses in suction pipe. Right, so this will be 100 plus PS by gamma, and V1 square by 2G is going to be 0.065 because V1 we have already found out. plus losses in the suction pipe is 0.174, major and the minor losses 033. This is major loss, this is minor loss. Okay, so PS by gamma can be found out to be minus 5.272 meter. Okay, this is gauge. All right, so the real pressure is going to be 10 minus 5.272 because we've already been told the absolute is 10, so it's going to be or equal to 4.728 multiplied by 9.79 to get it into form of kilopascal. So 46.29 kilopascal absolute. All right, this is the value that we have got. So both the answers we got. Now we proceed next and we solve one more problem, a very simple problem. We say a pipe enlarges suddenly from D1 is equal to 240 millimeters to D2 is equal to 480 millimeters and the HGL rises by 10 centimeters. Calculate the flow in the pipe. All right. So this is V1 and this is V2. All right, so this is 1 and this is 2. So we are going to solve this as well. So we can write Bernoulli's equation P1 by rho g plus V1 square by 2g plus Z1 will be equal to P2 by rho g plus V2 square by 2g plus Z2 plus whatever the head loss is. Okay, so we take V2 on this side, so we can write V1 square by 2g minus V2 square by 2g minus HL is equal to P2 by rho g plus Z2 minus P1 by rho g plus Z1. Okay. And all right. So to find the relation between A1 and V1, V1 and V2, we can say V1 A1 is equal to V2 A2. All right, which will give us, so areas are double, so we are going to get V1 is equal to 4 V2. All right, and if we put this in these equations here, and we also know that this is 0.1, that is what it says, that the HGL rises by 0.1. Therefore, this will become 16 V2 square, this equation here, by 2g minus V2 square by 2g is equal to 4 V2 minus V1 square by 2g, sorry, this is minus, because there was an entrance, you know, head loss is, what is this HL? HL is V1 minus V2 whole square by 2g. If you remember the minor loss formula, is equal to 0.1, and if you solve this equation, you are going to get 6v2 square by 2g is equal to 0.1, which will give v2 as 0.57 meters per second, implies q is a2v2, which will give 0.103 meter cube per second. Very simple formula. The application we have seen using Bernoulli's equation, equation of continuity, and because there is going to be a minor loss which is equivalent to v1 minus v2 whole square by 2g, as we have said, we have read in the minor loss the topic on the minor losses in the pipes. Okay. All right. So we proceed forward from this question. So we talk about pipe networks. Pipe could be connected in series or parallel, right, or combination of both. So this is a serial connection. So in the serial connection, the important properties are that discharge Q1 in this section 2, this section 3 will be the same. However, the total head loss will be the sum of the head losses of individual sections. Whereas in case of parallel connection, the discharge will be the sum of all three. So if there is a discharge Q, Q1, Q2, Q3, but the head losses will be the same in each of the lines. So this is the thumb rule, important thing to remember when you are dealing with pipe networks. All right. So a water distribution system consists of complex interconnected pipes, service reservoir and or pumps which deliver water from the treatment plant to the consumer. The water demand is highly variable, whereas supply is normally constant. Thus, the distribution system must include storage elements and must be capable of flexible operation. So pipe network analysis involves the determination of pipe flow rates and pressure heads at the outflow points of the network. The flow rate and pressure heads must satisfy the continuity and the energy equation. That is very true, as I told you in the last slide. The earliest systematic method of network analysis is called the Hardy-Cross method and is known as the head balanced or the closed loop method. So pipe network is a topic where we are going to study this famous method of Hardy-Cross method. It is known as the head balance or the closed loop method. It is a very systematic way which can be used for solving the pipe networks. So this particular method of Hardy-Cross is applicable to a system in which pipes form closed loops. Okay, so the outflow from the system are generally assumed to occur at the junction nodes. For a given pipe system with known outflows, the Hardy-Cross method is an iterative procedure based on initially iterated flows in pipes. So Hardy-Cross method has a set rule and procedure, but this for the solution it is an iterative procedure. So what are the important points to remember in solving pipe networks using Hardy-Cross method? That at each junction the flow must satisfy the continuity criterion. What are this continuity criterion? The continuity criterion is that the algebraic sum of the flow rates in the pipe meeting at a junction together with any external flows is 0. Suppose this is a node, right? There is Q1, Q2, Q3. So Q1 is equal to Q2 plus Q3. So the net outflow at any junction should be 0, is the continuity criterion. Secondly, the algebraic sum of head losses round each loop must be 0. So sigma of head losses in one loop like this should be 0. All right. So, with a simple continuity equation, we are going to solve one class question. The question is a pipe 6 centimeter in diameter, okay, here, and 1000 meter long and with lambda is equal to 0.018 is connected in parallel. So, this is pipe 1 and this is pipe 2 between 2 points M and N, all right, and this other pipe is 8 centimeter in diameter and 800 meter long. So, this was 1000 meter long, this is 800 and the diameter was 6 and diameter was 8 and this has a lambda of 0.020. A total discharge of 20 liters per second enters. So, from here something 20 liters per second enters the parallel pipe through division at A and rejoins at B. So, it here and it rejoins here. Estimate the discharge in each of the pipe. Very simple application of the concepts we have learned till now. So, we are going to solve this question. All right. So, there was pipe, right. So, Q will be equal to Q1 plus Q2. So, total discharge is 0.02 and we know the areas pi by 4 into 0.06. Let us say velocity is V1 here and in the pipe 2 it is V2, 0.08 V2, all right. So, this is the equation for the continuity equation for discharge, all right. So, for pipes in parallel, we also know that the head losses should be equal in both pipes. So, this actually can be written as V1 plus 1.778 V2 is equal to 7. If you solve this, it will come this. This is the one equation that we have got from here. And now, HF1 is equal to HF2, which means lambda 1 L1 V1 square. This is the major loss in pipe 1 is equal to lambda 2 into L2 into V2 square by 2G D2, all right. So, let us substitute the value. Lambda 1 was 0.018, length was 1000 first pipe into V1 square by 2. So, 2G D1 is comes out to be 0.06. This will be 0.020 into 800. This comes to be 0.08 into V2 square. So, taking it here, we will get V1 is equal to 0.8165. So, we have two equations in V1 and V2. So, 1 and 2. Solving for V2 by substituting 2 in 1, we will get V2 as 2.73 meters per second. So, Q2 will be A2 V2. So, pi by 4 0.08 whole square into 2.73. So, Q2 will come to be 0.0137 meter cube per second. Now, if we know V2, we can get V1 from here. V1 will be 0.8165 V2 this will give us V1 as 2.23 meters per second, and therefore Q1 will be A1 V1 will give us 0.0063 meter cube per second. All right, this is the answer, but one important step is it's better if we recheck the answer. Recheck the answer by Q1 plus Q2 if it is equal to Q or not. So 0.0063 Q1 plus 0.0137, it is coming out to be 0.020, which is equal to Q. So our answers is okay. So this was one other question. Now the one more question is, there is a horizontal pipeline which is 50 meters long and is connected to reservoir at one end and discharges freely into the atmosphere at the other end. So for the first 25 meters I have shown this diagram here. Okay. All right. So the first 25 meters length from the reservoir, the pipe has a diameter of 15 centimeter and it has a square entrance at the reservoir. The remaining 25 meter length of the pipe has a diameter of 30 centimeters. So this is the long pipe. Okay, and this is pipe 1, and I mean the things that we were talking about. Diameter is different here, diameter is different here. So junction of the two pipe is in form of a sudden expansion. So we have been told sudden expansion. That means there is going to be a energy loss, minor loss. It's also told that there is going to be a gate valve in a 15 centimeter pipe. So there is going to be another minor loss here. Okay. So if the height of the water surface in the tank is 10 meter above the center line of the velocity, estimate the discharge in the pipe by considering the Darcy-Weisbach friction factor of 0.02 for both the pipes. So this is given because there will be also major losses between these two sections, major losses. Okay. So we have to, this is a complete question that involves both the major and the minor losses. All right. So we are going to actually I think this is a nice point to stop. In the next class we are going to solve this particular question in detail, because then it will be fresh in your mind. And then we will proceed to our last topic, that is Hardy-Cross method. So thank you so much for listening. I will see you in the next lecture.